Hi, it's Mr. Baker here. Today we're going to be looking at distance time graphs. Okay, so today we're going to be looking at distance time graphs, and we're going to be answering this question. Can you tell a story with a graph? Right, before we start, we need to know a few words. We looked at these in the last lesson when we looked at speed. I want to see if you can link these up. So I'll give you a couple of seconds. You might want to pause the video. You might want to jot this down, see if you can do it. And then I'll tell you in a second. Okay, did you do that then? So let's have a look at the answers. Okay, so distance is how far an object moves. Displacement is the distance in a particular direction. Speed is the distance travelled in a given time. And then velocity must be the distance in a particular direction in a given time. Hopefully you got all of those. Really, really important that you know the differences between those. Okay, so have a look. This is an example. We've got two distance time graphs here drawn on the same axes. So a distance time graph, what you have is the time along the x-axis, and you have the distance on the y-axis. Now time, we always measure in physics, we measure time in seconds, and distance, we always measure it in meters. Now potentially you could have different units if it's more sensible on your axes, but that would be the standard units. The standard units would be time in seconds and distance in meters. And you can see we've got two different graphs we've drawn on these axes here. So we've got a red graph that follows that, and we've got a blue line there. So we can get the following information from a distance time graph. So we can find the total distance travelled for an object, whatever that object might be. We can find the average speed of the object. We can find the type of the motion, so I can say whether it's going at a steady speed, if it's stopped, if it's accelerating, if it's slowing down. I can even tell you the direction that it's going, and I can tell you the exact speed at a different instant. So at any instant on a distance time graph, I can tell you, so in other words, at any time on the distance time graph, I can tell you the speed that it's going. So what it's really doing, what a distance time graph does, in a way, is it tells a story. It tells a story of an object and how that object moves. It tells us whether it was going forwards or backwards, if it was going fast or slow, if it was speeding up or if it was slowing down, if it was stopped, and it tells us how that object's motion changed over time. So this could be the story of somebody who is late for something, and they have to sprint 10 meters really quickly. Maybe not a person actually, because the time is only 2 seconds. It's taken them to go 10 meters. No, that's all right, isn't it? You can go 10 meters in 2 seconds. In fact, that would only be 5 meters per second, wouldn't it? So yeah, that could be a person maybe jogging, or maybe quite a fast run. They're going 10 meters in 2 seconds. So from that then, I know that the total distance that they went was 10 meters on this graph here, and I know it took them 2 seconds, because that's the 2 points I can see from that graph. If I want to find out the speed, now the speed is the distance divided by the time. It's the that's what we describe speed as, isn't it? So the distance over time. So actually from what we already know, I can find out the speed. The distance they travelled in total was 10 meters. The time was 2 seconds, so 10 divided by 2 is 5 meters per second. So you can see that actually from the graph anyway. In 1 second, look, they went 5 meters. So that's what I mean by the speed. If I'm looking at it as of a unit thing, I went 5 meters in 1 second, so the speed was 5 meters per second. Okay, I also know that these two objects, whatever they might be, the blue one was going faster than the red one. So I can compare the speeds of different things as well, potentially. So this other object, it could be somebody who was walking, and then they were walking along, patted their pocket, went, oh no, forgotten my keys, and then walked back towards the house to get their keys. Don't know, it could have been more exciting, could have been less exciting, but it could be anything. But it's basically something that's moving away from the origin, away from the starting point. They moved away, and I can tell you what the speed was because they went 8 meters in 4 seconds, So 8 meters in 4 seconds, 8 divided by 4, they were moving away at 2 meters per second. So it wasn't a slow walk, it was, it wasn't a fast walk particularly, but it was 2 meters per second. Then they stopped, they got 8 meters away from where they were walking from, and they stopped for 3 seconds. So they stopped for 3 seconds. Another word for stopped is stationary. They stopped for 3 seconds, and then they went back towards the place that they were at. So they were at 8 meters away, and they went back to 0 meters away. So they went back towards where they started from, and they went 8 meters in 3 seconds. So 8 meters divided by 3. 8 meters divided by 3. So 2.67 meters per second, but it was minus 2.67, wasn't it? Because they went back to 0 and they started at 8. So if I was finding out the difference between those, it would be 0, take away 8, minus 8, over 3 seconds. So minus 8 divided by 3. So their speed was minus 2.67 meters per second. In other words, they're going backwards at a speed of 2.67 meters per second. Okay, so they went back quicker than they went away in the first place. So they walked, and this one was 2 meters per second, wasn't it? They stopped for 3 seconds, and then they went back at 2.67 meters per second. Okay, so you can tell all of those different things from that. Here we've just got straight lines as well. So straight lines tell me that it's always constant. So a straight line tells me that the speed is steady. So that's quite easy. It's just saying that it's always going at a very steady speed. And in physics we use models a lot. Obviously somebody who's walking probably wasn't exactly steady all the time, but we're saying that their speed was going at the same speed all the way along. Okay, so that's how you can tell a story with a graph, and you can tell quite a lot of information from that graph. Let me show you some different things that we can do. So you might want to take some notes or look at this. This is useful stuff here that you will need to understand. So look, something going at a slow constant speed might have a fairly shallow gradient there. Something that's going fast constant speed will have a steeper gradient. So the gradient is basically how steep the line is. So that's not very steep, so it's slow. That's steeper, so it's faster. Okay, slow and then fast. So the slope or the gradient of a distance time graph shows us the speed. Okay, if something's speeding up, it's not going at a constant speed or a steady speed, it's speeding up. That's the definition of what's happening. So it's changing speed, and so if something's speeding up, it's not going to have a straight line. We said in just a second ago that when something's going at a steady speed, it's going to have a straight line. So when something is not going at a steady speed, it's going to have a curved line. And so something that's speeding up, that's accelerating, would look like that. Something that's slowing down would look like that. Now, this is sometimes something people find a little bit tricky, because maybe you'd think if something's slowing down, the line would be going down. But look at what's happening to the slope or the gradient in both of these cases. So we've just said that the slope can tell the speed. So if I draw a tangent of a curved graph, that shows me the speed as well. And so what I mean by tangent is something like that. So a tangent, I'd take that point there and I'd draw a straight line. So as if that line just carried on at that point, straight up and at that angle, that's the tangent just there. So if I drew that tangent there, then I could work out the gradient there. I could find the speed from working out the gradient of the tangent. And you can see, look, at that point there, the gradient or the slope is that steep. At this point here, the gradient is this steep. So I know that the speed is changing because the gradient is changing, and I know that the gradient tells me the speed at a particular time. So the first tangent, so that was that one, has a larger gradient, so it's got a larger speed. the second gradient has a smaller gradient and therefore it must have a lower speed. So the graph shows that the object in this case is decelerating. Yeah, so this is decelerating because it was going faster and then it was going slower. So that slope tells me the speed, and over time that slope has got smaller, and so the speed has got smaller, and that's what we mean by decelerating. Something that's slowing down, the speed is getting less over time. Okay, so a little challenge for you then. So have a look at these things here. What are each of the things on the graph doing? So we've got this person here, not actually sitting on this line, but this is just showing you that this is the person's line. So this line here is for the person. We've got 3 lines that are different lines for a car. So we've got this blue line here, which is a line for the car. We've got this red line here, which is another line for the car. And we've got a black line here. So 3 different lines for the car. And then we've got this blue line here for this plane. And we've actually got a bit of information here for this plane as well. So I would like you to basically, first of all, I want you to, after I've stopped talking any second, pause the video and describe what is happening, what's the person doing, what are the 3 lines for the car, what do they show, what does this line for the plane show, and then you can also find what speed that plane was going, and maybe you'll know how fast you need to go to create a sonic boom as well. Okay, so pause the video, maybe jot them down, and I'll tell you the answer in a sec. Okay, so did you ever get that? So this person, the distance isn't changing, is it? The distance is just staying flat, so they are stationary. They haven't moved. In all of that time, they hadn't moved. Car for the blue line, they were moving away slowly in the car, so it's a steady speed moving away. The black line, steady speed again, but moving back towards wherever they started from. And then this red line shows that the car was moving away and getting faster, it was accelerating over time. And then the plane then. So the plane was moving away quickly. And how quickly? Well, 170 is the distance divided by 0.5, 170 divided by 0.5, what's that? 340 meters per second. And maybe you know how fast do you need to travel for a sonic boom? Well, you need to travel at the speed of light. You need to break this, sorry, not the speed of light, the speed of sound. You need to travel at the speed of sound, or quicker than the speed of sound. The speed of sound is about 340 meters per second. So that plane, if it was traveling at around the speed there at 340 meters per second, it might be just going fast enough to get faster than the speed of light, faster than the speed of sound, and breaking that sound barrier and creating a sonic boom. So that's almost the end there. So these are the things you should be able to do from today's little lesson. You should be able to describe how the gradient of a distance time graph represents the speed. You should be able to use the gradient of distance time graph to compare the speed of objects and describe the motion of objects. You should be able to calculate the speed of an object and the time taken to travel a given distance, and you should be able to tell a story with a graph. Okay, so that is the end of this lesson on distance time graphs. Thanks very much for watching. I've been Mr. Baker, and I will see you next time. Thank you.